Okay, so we're going to do these collision problems. I'm actually going to start down here, do these ones first, and then come back to this example, which is actually a little bit more of a total problem. But all right, so we'll start down here. Ball carrying 1.5 kilograms times meters per second moving to the east. So that's this one. Its momentum is 1.5 kilograms times meters per second, mass times velocity. Collides with the ball carrying 2 kilograms, P2, of momentum to the west. So traveling to the left here. Sometimes we use left, right, east, west, doesn't matter. I'm putting a negative sign in front of it because that's going to be important when we try to show the conservation of momentum. This is a system, these two objects. It's a system. And the total momentum of the system will remain constant before and after the collision. All right. After the collision, ball 1 bounces backwards, so P1 after the collision is negative 0.20. Whatever direction, the direction of the velocity equals the direction of the momentum. All right, that's an important note there. Direction of the velocity is always the direction the momentum is in. Moves with momentum, mass times the velocity. In ball 2, we don't know what's going to happen, right? Might bounce backwards or it might just keep moving forward. It might give some of this momentum and keep moving forward. We'll see. All right, so it says part A, determine the total momentum of the system before the collision. So P total, all right, we usually don't write down P total by itself, is going to be simply equal to P1 plus P2. And that could either be before the collision or after the collision. If you know the momentum before the collision, that's what the momentum after the collision has to be equal to. So we're going to have, it's going to be mass 1. So remember, P equals mv. So it's going to be mass 1, or sorry, we don't need to multiply that, that's my bad. We already have the momentum, so it's 1.5 kilograms times meters per second plus momentum 2 is negative 2.0 kilograms times meters per second. So plus a negative number is the same as subtracting, so the P total before the collision is, I guess maybe that's how I should write it, just P before equals this, negative 0.5 kilograms times meters per second. Determine the momentum and direction of motion of ball 2 after the collision. So P before has to equal P after, right? So the momentum before is simply the negative 0.5 kilograms times meters per second. The momentum afterwards is P1 plus P2 after the collision, so it's going to be the negative 0.20 kilograms times meters per second plus momentum 2. Now we can do the algebra here, right? We add 0.2 to both sides, plus 0.2 plus 0.2, we get negative 0.3 kilograms times meters per second equals P2 after the collision. All right? So momentum of object 2 after the collision has to be negative 0.3 kilograms times meters per second because it has to add up to be negative 0.5, the total momentum. So P2 is actually going to keep moving forward. It's just going to really slow down, right? So they're coming in, P2 hits, it's slow, P1 momentum, or sorry, object 1 gets turned around, object 2 keeps moving forward slowly. All right, so if ball 2 has a mass of 0.2 kilograms, how fast is it moving after the collision? How fast? That's v, right? So P equals mv. Now we can use that equation. We know that its momentum has to be 0.3 kilograms times meters per second. We know its mass is 0.20 kilograms now. All right, so the velocity is unknown. So we divide both sides by 0.20. We're going to get V of ball 2 after the collision is negative 1.5 meters per second. We don't know how fast it was going initially, so there we go. All right, page 1 is a different problem now. Page 2, we've got 0.5 kilogram block slides to the right at positive 2 meters per second, collides with the 1 kilogram block that is initially at rest. 0.5 kilogram block bounces backwards, and the large block moves in the direction. So I gave you the initial drawing. I didn't give you the final drawing. So I'm just going to that one goes off that way. This one goes off this way after the collision. Set up the conservation momentum equation. Set the total initial momentum equal the total final momentum. P before the collision equals the momentum after the collision. All right. The small block. So before the collision, all right, we'll call this 1 and 2. We got P1 plus P2 equals P1 plus P2. Momentum before and after. I don't like to put subscripts and everything. You know, this side's after the collision, this side's before the collision. They have to be equal to each other so that momentum is conserved. Now P2, right, since initially the velocity is 0, momentum initial for P2 is 0. So all we have is P1. So P1 is M1 times V1. All right, so it's 0.50 kilograms times positive 2.0 meters per second. That's 1.0 kilograms times meters per second. All right. After the collision, that's M1 V1. This is M2 V2, or P2, wherever you want to say. We don't know what P2's velocity is afterwards. It's got to give us enough momentum to add to this one to give us 1. So M1 V1 after the collision, it says it's still obviously 0.5 kilograms. The velocity after the collision, it says it bounced backwards, right? So velocity after the collision is negative 0.25 meters per second plus P2, I'll just call it. We don't know what that momentum is. So 0.5 times negative 2.25 is negative 0.13 kilograms times meters per second. All right? So if the initial momentum is positive 1, but then P1 bounces backwards, that means that P2's got to be positive, and it's got to be big enough so that when you take away 0.13, it will give you 1. So basically, using the conservation we just set up, determine the final momentum of the big block. So that's positive 1.0 kilograms times meters per second equals negative 0.13 kilogram times meter per second plus P2. Add 0.13 to both sides. You get P2 must be positive 1.13 kilograms times meters per second. So this one bounced backwards at negative 2.5 meters per second. This one gets shot forward at 1.13. Or sorry, we don't know yet. My bad. Determine the speed of the big block. So now we can say P2 equals M2 V2. So positive 1.13, mass 2 is 1.0 kilograms. Well, it does come out. I thought it did. That's why I was. Divide both sides by 1.0. You get a final velocity of block 2 of positive 1.13 meters per second. So it is positive 1.13 meters per second. All right, so that stationary block picks up a bunch of momentum. All right, now we're getting into the ones that are the full-on problems. In this video, I'll probably do a couple of them, and then I'll make a second video to deal with some of the other ones. The other ones. I'm going to run out of time here. So 1 kilogram block slides to the right. So I always like to draw a really quick picture. 1 kilogram, 1.0 kilograms slides to the right at 2 meters per second. 2.0 meters per second. Collides with a 0.5 kilogram, 0.5 kg at rest. two blocks stick together, so they become one object. All right, and then we want to know how fast it ends up moving. We know it's going to have to move to the right. That's kind of common sense, right? The big one comes in, sticks to that other one, and then they keep moving. And we've seen in demonstrations in class and in the simulations, when this happens, the system, the block, the incoming block, its velocity goes down because it's picking up more mass. So P before equals P after. So this is, we're freeing ourselves from this part A, part B, part C at this point, right? So we're going to just say the total momentum before has to equal the total momentum afterwards. So that means that M1 V1 plus M2 V2 before must equal M1 V1 plus M2 V2 afterwards. So the sum of the momentums before the collision must equal the sum of the momentums after the collision. So we've got 1.0. I'm not going to put the units in here because I drew them on the diagram and they just get kind of messy in there. This one here, the velocity V2 is 0, right? So that one's just 0. After the collision, what I like to do, look at V1 and V2 after the collision, they're going to be one object. What I like to do with this is think of it as actually just the total mass added together multiplied by the speed of the object together, right? I think of it as being one object after the collision, right? We don't have to write it as separate objects because actually V1 and V2 have to be equal to each other. So it's like M1 times V, let's say, plus M2 times V, and you factor the V out. All right, so there's that. So we've got 2 equals 1.5 times V, divide both sides by 1.5. We get V equals 1.3 meters per second. And it came out positive, right? It did come out positive because this is positive, this is positive. It's positive 1.3 meters per second. All right, I'm going to do one more page here for now, and then I'll start a second video when I get time later. All right, so 0.5 kilogram block traveling to the right, collides head-on with a, so this is kind of like, so 0.5 traveling to the right, so that's positive 15 meters per second, collides head-on with a 0.3 kilogram block traveling to the left at 12 meters per second. That would have to be negative. Before, after the collision, 0.3 kilograms, so we start with this one, bounces backwards. So it bounces backwards at 11 meters per second. Right? And we don't know what happens to the 0.5. Maybe it slows down, maybe it turns around and goes backwards. But I should have left myself a little more room here. I want to show you, I typically just jump right into the numbers and I'll go, okay, this one's momentum, 0.5 times positive 15 plus 0.3 times negative 12. So that's your total initial momentum. After the collision, it's 0.5 times the unknown velocity. We don't know what the velocity is of this one. I don't put a sign on it because I don't know which direction it's going to move in yet. Plus 0.3 times positive 11. Bounce backwards, so that's going to be positive now. So we just plug and chug the math here. Once you get the hang of this, these problems are really pretty simple. Because it's just always conserved. I missed the negative sign. Oops. Times negative 12. So we've got 3.9 on this side equals 0.5V plus 3.3. So we subtract 3.3 from each side. Right? 3.9 minus 3.3 is 0.6 equals 0.5V. 0.6 divided by 0.5 is 1.2. and it came out positive, right? The signs matter. It came out positive in the end, 1.2, positive 1.2 meters per second. All right, I'm gonna stop this video here. I will get this posted and then do the last 3 problems for you. These are good ones we're gonna go over in class today.